Hi everyone, my name is Sejong and I'm a research engineer at the AI Labs of Edge Electronics. Today I will be talking about work what I did called Deep Active Learning for sequence labeling based on diversity and uncertainty in gradient. Sequence labeling is widely used in natural language processing tasks like named entity recognitions and slot filling tasks for various fields. And it already seems to be showing successful performance with deep neural network. However, it relies on a large amount of annotated dataset for having a high performance model. Unlike the classification task, its labeling annotation is required for an entire sequence. From the example of annotations for two tasks in bottom of page, it needs an annotation for each word. As we all know, the annotating process is a time-consuming and expensive task. For the industry, this problem often be a bottleneck of serving the high-performance model to the customer. So we handle those problems with active learning to achieve high performance with low labeling cost. In the idea of active learning, this goal is having a high performance model possible given a fixed number of label data. The diagram is process of active learning and different status of dataset we have. We are going to follow each step of the cycle. At the first, we are going to train our model with an available label dataset. This model will be used by selection function to find the implemented dataset. And then you have some function to select a batch of unlabeled data samples with a pre-trained model. The reason why we select a batch of multiple samples is instead of one at a time. It is more efficient for time and computation cost. After labeling those samples, it is integrated into the label dataset. Then this process is repeated until it meets an expectation. To achieve high performance with a low labeling task, cost is important to select the most representative and informative sample. From this aspect, there are two major approaches for active learning, namely uncertainty-based sampling and diversity-based sampling. Uncertainty-based sampling approaches are selecting a batch of samples that the model is uncertain about its measurement. It has been the most successful and commonly used in NLP tasks. Especially Bayesian-based approach shows outstanding performance in the NER task. However, in batch active learning, it is a lack of diversity in samples is likely to select relatively similar to each other. On the other side, there are diversity-based sampling approaches, and these occurring diversely throughout the unlabeled dataset by using representation space of the neural networks. Its goal is selecting a representative dataset which explains the unlabeled dataset well. However, this approach might select points that provide little new information, thereby reducing the uncertainty of model. So in this work, we focus on integrating diversity and uncertainty into a selected batch, which is advantageous to each other over different dataset and architecture. So we adopt a previous work, batch active learning by diverse uncertain gradient, which called batch. It shows a robust improvement of our image classification task. However, Its performance in sequence labeling task is not yet proven. Additionally, we consider the cost of labeling is proportional to the length of the sentence in the sequence labeling task. So we suggested a method to expand batch with weighted sampling based on the sequence length to ensure cost-effective labeling. We named it as a weighted batch. And so we can summarize weighted batch active learning for two main computation processes. First, extracting gradient embeddings from parameters of final layer for our unlabeled data samples, and sampling a batch of query points based on those gradient embedding using the weighted sampling method. It selects sentences for which the diversity and uncertainty are high when considering its reverse length. We explain its computation steps more detail. This is details of computing gradient embedding in sequence labeling task. Model predicts the hypothesis label y hat for each token. Then computing rows with those labels, we compute the parameters in the last layer of network and treat gradients as embedding. As sequence labeling has a time step, it computes over time step and comes out the summation of its value. Those embeddings have a magnitude based on probabilities of prediction and include penultimate layers information. Previously acquired gradient embedding, if the model is uncertain to data, the magnitude of embedding will be relatively high. To capturing the both uncertainty and diversity, sampling is needed for finding samples which current model is uncertain about and are different each other. Batch applying k-means initialization algorithm samples to k-centers to select high magnitude and independent sample. To consider the cost of annotation, we modified the probabilities to sample new data center with the sequence length. From this simple tweak, our approach is more likely to select a sample which have higher uncertainty as well as proportion to reverse length. For the experiment, we used three publicly available datasets: Cornell for NER task, APTIS, and FACE for multilingual task-oriented native English version for slot tagging task. The bottom side of the table shows the description of each dataset. Slot filling task tends to have more number of class because of its characteristic of task. And we used two architecture for training, one for Bayer stem tagger without decoder, and the other one is a Bayer stem encoder decoder. Their architecture is similar but have difference in depth. It is widely used architecture for sequence labeling task. Before starting active learning procedure, we assume that there is no labeled training dataset. So first we define a sampling budget. There is a number of samples to be labeled by active learning round. To begin with procedure, we randomly select the labels that n% of samples, which is the predefined budget, from the dataset for training initial model. As we introduce procedure in introduction, our experiment repeated of active learning procedure. As the first, training the model with a label dataset. Second is the querying a predefined number of samples from an unlabeled dataset. Last one is the adding it to the training dataset with a label. This procedure is repeated until meet our expectations. And here I'm showing the result of different active learning experiments using the 3 datasets and 2 architectures and 6 baseline algorithms, including random sampling. Some of them are uncertainty-based sampling. The other is diversity sampling and hybrid approaches. Our experiments are repeated 5 times, and average performance scores reported as a line, and the standard deviations are indicated by shaded. From the result, we can see that blue lines of weighted batch outperforms on Cornell dataset for annual task over other baseline algorithms, including previous best algorithm and batch in different architecture. And then we also experiment on other dataset for slot tagging task. Weighted batch also shows improvement to varying degree. In artists, weighted batch outperform over the other baseline. For the Facebook multilingual dataset, hybrid approach performs better than other approaches, but similar each other in biased integer model. However, weighted batch shows slightly improvement over batch and other baseline in BiLSTM encoder-decoder architecture. We observed that the weighted batch method indicated a significant improvement or performs as well as over the baseline active learning method. Also, it is notably reduced a number of required datasets in achieving performance. For example, we found that weighted batch achieve a 98 to 99 performance of model trained on full data using only 15% of samples in artists. Finally, I would like to conclude by saying that we have provided an empirical evaluation of active learning utilizing the advantages of both uncertainty and diversity for synchronous learning tasks using different models. We propose a cost-effective method, weighted batch, and demonstrated that it could be consistently superior performance while consuming much less data. It could be a useful option for solving real-world active learning problem regardless of dataset. However, it still remains limitations in our approaches. First one is a cold start problem. Approaches like a batch often rely on uncertainty measured by trained model can be unreliable if model has not trained well. Second is computation inefficiency. Selecting diverse gradient embedding requires a high computation cost. As the dimension of gradient embedding is related to size of layer and the number of labels, it is likely to require expensive computation cost. So in the future, we plan to investigating more efficient algorithm to adopt it for real-world setting. Thank you very much for listening.